You know how most engineering projects go, right? You design a system, you tweak it to optimize performance, and then you just hope it's competitive enough to work. Well, today we're going to look at a framework that completely flips that logic on its head. What if superior performance wasn't something you had to design for at all, but something you could select for right from the very beginning? Okay, let's really break this down. The idea is simple, but it's a real game changer. On the left, you see the traditional path. It's linear and it's full of uncertainty. A shot in the dark, really. But on the right, you see a totally different way of thinking. It suggests that for a very specific class of systems, like energy co-production, if you just select for the right structural conditions at the start, amazing performance isn't just possible, it's pretty much inevitable. The whole challenge shifts from designing a system to selecting the right conditions. So here's our game plan. First, we're going to dig into what it means to invert the design problem. Then we'll go through the four-axiom checklist. This is your go/no-go guide. After that, we'll look at the hard data from 5 different real-world examples. I'll show you a super fast screening tool you can use right away. And finally, we'll tackle those big questions around sovereignty and compliance. Right, so let's get to the heart of this. The big idea here is that some systems have a kind of economic physics built right into their DNA. If you can spot that underlying structure, incredible performance isn't just a possibility, it's practically guaranteed. And it's got almost nothing to do with how well you manage it day to day. This completely reframes the job, doesn't it? It says that success isn't about working harder to fix a flawed system. It's about finding projects where the very structure gives you a massive, almost unfair advantage. And look at that third point. The key performance driver isn't your management skill. It's the opportunity cost of your input, what the paper calls P0. In plain English, that's the market price of your main resource, like surplus energy. The closer that price is to zero, the higher your performance. So your most important job is no longer being an operator, it's being a selector. And this quote just nails it. It perfectly captures that new role for management. You're not there to create value out of thin air. No. The advantage is already there, baked into the system structure. Your job is simply to capture that advantage and turn it into a financial result. It's a really powerful shift in mindset. Okay, so how do we actually find these systems? Well, this framework gives us a super practical tool, a non-negotiable go/no-go checklist. It's a filter for any decision maker looking at a new project. And the rule is simple. If a project doesn't pass all 4, you just stop. Axiom number 1 is the foundation of everything. Is your main input essentially free because it would otherwise just be thrown away? You know, we're talking about things like hydroelectric spillage from a dam, wind power that gets curtailed, or waste heat from an industrial plant. The test is dead simple. Are you using something valuable that everyone else is treating like garbage? Axiom 2 is about being a value multiplier. From that one single zero-cost input, you have to create at least 2 independent streams of value. Now, that word orthogonal is key. It's just a fancy way of saying they don't compete with each other. Selling more AI compute power doesn't stop you from selling electricity to the grid. They're like 2 separate businesses running on the same engine. Axiom 3, this is where the financial magic really happens. The huge capital investment, for the dam or the wind farm, it's already there. It's already been paid for. That's a massive economic advantage because you're adding whole new revenue streams by just piggybacking on infrastructure that's already in place. And finally, Axiom 4 is all about making sure you're riding the right wave. That term shadow price just means the true market value of something. So this axiom says you have to be confident that the markets for all of your outputs, in this case, both AI compute and renewable energy, are on a long-term growth path. You're not betting on today's prices, you're betting on a strong rising trend. So the theory sounds great, but does it actually hold up in the real world? This next part is where we move from the framework to the hard data. We're going to see how this model performs across completely different industries and locations. This is the question that any smart investor or engineer should be asking, right? It's one thing to have a slick theory on a slide, but it's a whole other thing for it to actually work when the rubber meets the road. So let's see the evidence. So this framework wasn't just tested once. It was validated against 5 completely independent real-world scenarios. And that diversity is so important. It's what tells you that we're looking at a fundamental principle, not just some weird one-off result. And here it is, the proof. This table shows the value multiplier, which the paper calls phi-ox, across those 5 different domains. I mean, look at those numbers. We're seeing multipliers from almost 9x all the way up to a mind-blowing 27x. But you know what? That's not even the most important number here. The paper shows that the net margin, the actual profit, is incredibly stable across all of them. It only varies by about 24%. And that is the smoking gun. It proves that your performance is set by the global compute market, not by your local energy conditions. This quote just summarizes it perfectly. The big takeaway from all that data is that the value isn't tied to the specific source of that surplus energy. The value is created when you convert a wasted electron into a valuable bit of computation, because the market for those bits is global, and that's what sets the price. All right, so we've covered the theory and we've seen the proof. Now let's get really practical. This next section is all about how you can take this framework and turn it into an actionable tool for you and your team, like tomorrow. Believe it or not, you can evaluate a brand new project in about 75 minutes using this two-step process. Step 1 is a quick 15-minute check. Does the project meet all 4 axioms? You can usually figure this out with public data. If even one answer is no, you stop right there. Think of the time you save by killing structurally bad projects early. Now, if it passes, you move to step 2. About an hour to calculate that value multiplier, phi. If that number comes out at 10x or more, you've got a really strong candidate that's worth a proper deep dive. And when you find one of these projects, it completely flips how you think about risk. This is what the paper calls the impetus criterion. All of a sudden, the biggest risk isn't moving too fast, it's waiting too long. When the structure is this good, the cost of just sitting on your hands becomes enormous because you're leaving value on the table that you can never get back. Of course, no project lives in a bubble. We have to talk about a major concern, especially for anyone operating in Europe. What's the real-world impact of all the regulations like NIS2 and the EU AI Act? Well, here's the crucial thing. The model's strength was actually tested against these regulations. The costs of full compliance, data sovereignty, all of it, they were modeled as a cost shock to the system. And the result? The financial viability holds up no problem. The additional costs are just easily absorbed within the model's huge performance envelope. These projects stay incredibly profitable. And this is a brilliant way to reframe the entire issue. That regulation isn't just a cost you have to swallow. It's a strategic tailwind. Think about it. These rules are creating a permanent, policy-driven demand for the exact kind of sovereign, secure AI compute that these systems produce. So compliance isn't a hurdle, it's a durable competitive advantage. So let's end with one final kind of provocative thought. The paper projects something called a climate dominance crossover point, right around the year 2059. That's the moment when the value created by the system's CO2 avoidance, another one of its co-produced value streams, is projected to actually be worth more than the revenue from the AI compute itself. It forces you to ask a much bigger question. Are we just building compute assets that have some nice climate benefits, or are we actually building the climate infrastructure of the future that just happens to be financed by compute for the first few decades? Something to really think about.